For centuries, mathematicians have tried to find perfect ways to describe complex shapes and functions using simpler building blocks. One of the most common tools is the polynomial, those familiar expressions from algebra class. While they are great for smooth curves, they really struggle to accurately capture functions with sharp corners, like the letter v or other odd behaviors. Getting a good fit often takes an enormous, impractical number of terms. Recent breakthroughs showed that by layering polynomials on top of each other, much like layers in a deep neural network, we can create deep polynomials. These structures are surprisingly good at learning those sharp corners, closing a long-standing gap in approximation theory. But the researchers behind this paper asked, what about functions that are even weirder? Think of a function that has a sharp point but also shoots up to infinity on one side while quickly fading to zero on the other. This mix of local spikiness and global extreme behavior is a massive challenge for most mathematical tools. To solve this, the researchers developed a clever new approach they call a weighted deep polynomial approximant. It's a hybrid tool with two key parts. First, it uses a flexible deep polynomial, which is great at capturing the fine-grained, local details of the function, like any sharp turns or wiggles. Second, it multiplies this polynomial by a specially chosen weight. This weight acts like a guide, taming the function's wild global behavior by managing its tendency to grow or decay dramatically. By combining these two elements, they created a single tool that can handle both local complexity and global extremes simultaneously. To see if their idea worked, the team put it to the test. They compared their new method against several traditional techniques, including Taylor and Chebyshev polynomials, as well as the standard deep polynomials. The results were clear. The new weighted deep polynomial method was significantly more accurate than all the others, even when every method was given the same number of parameters, or the same amount of brainpower. They also developed a stable and practical method for training these models, making them ready for use. So, what does this mean in practice? This is more than just a theoretical exercise. The ability to accurately model functions with such extreme and asymmetric behavior is critical in many scientific fields. In physics, it could help describe complex quantum states or fluid dynamics. In finance, it could lead to better models for highly volatile assets. Essentially, anywhere that scientists or engineers need to create high-fidelity computer models of complex, real-world phenomena, this new technique could provide a more powerful and precise tool. If you enjoyed this breakdown, don't forget to like, comment, and subscribe for more AI research made simple.